Hello, everyone. Thank you for joining us at this version of the seed funding seminar. This time, we're lucky to host Dr. Qiang Huang, who for the past 4 years has been a senior lecturer in computer science at the University of Sunderland. His research covers several areas of multimodal information processing and deep learning. And this time, he will be speaking about improving anomaly detection in microscopic images of integrated circuits using deep learning technologies. The talk will go on for about 20 minutes, and then we'll have about 5 minutes of questions and answers in the end. Thank you.
Okay. Thank you, everyone. Good afternoon, everyone. And so my name is Qiang Huang. And so currently I'm working as Alex said, currently I'm working as a senior lecturer at the University of Sunderland. So this afternoon, I will introduce our work on the anomaly detection in microscopic images of integrated circuits using deep neural networks. So currently, the research on the anomaly detection is widely applied into the many research fields. So here you can find at least some research fields related to anomaly detection. The first is industry. So you can find this image, by using anomaly detection technologies. So some the potentials, faults and cracks, even the rust on the component in a machine can be found. The second thing is the cybersecurity. So this means many the potentials, anomalous behaviors, internet behaviors caused by hacker can also be detected by using the anomaly detection. And other things like the health, so this the image you can find is related to the diabetic retinopathy, and even like the X-ray images about the human's organs and the bones can be used to find the potential risk related to the human's health. So other things like the anomalous activity detection, and even some of the anomalous behaviors on the internet can also use anomaly detection technologies to find to stop to prevent some of the potential risks. And so due to the research AI hub that April, so our aim in this project is to develop some of the anomaly detection the skills technologies to detect anomalies in the integrated circuits. So why we want to do this? The reason is we know currently the integrated circuit is very important to the computer science, not only the computer science in this field, but also the many research fields or the fields need to use the computer science technology or use computer itself. So we hope the anomaly detection can help us to ensure the quality, reliability, and the performance of the semiconductor the production. So we know, and in order to produce the integrated circuits, currently we know the size of the integrated circuit is quite small. However, so the billion transistors need to be placed in this small size and the IC. So in order to avoid the potential risks, I mean when they produce this the chip size. So in order to avoid the potential risks, so generally they need to use some technologies to scan the structure of the chip site and try to stop, prevent the potential issues. So one of the ways is to use, for example, to generate the high resolution, the microscopic images. So by using image processing technologies, so the factories the companies, they can relatively easy to find the potential risks. So based on this background, so we want to use a deep neural network to improve the effectiveness and the efficiency in this field. So this slide shows the flow chart. The flow chart and shows the architecture of our used in our project current work. So certainly the first part, the left part, is the convolutional layer-based deep neural network. So you can find there are many several layers. Here just the example. So certainly, and if we use a deeper deep neural network, I think there should be more convolutional layers, but also including other layers like the batch normalization, activation, these layers, and even other specific layers in order to improve the performance. So unlike the traditional way of only using the output of the deep neural network, so in our work, we try to use the information from the multiple layers. So this is the reason is we think the information from not from the other layers. I mean, not only from the output layer. So the more key information could be included in order to improve the effectiveness of the system. Moreover, so for this work, currently the data set we are using is relatively limited. So in order to fine tune this deep neural network, so this easily causes some issues. So we think by only using the output layer, so we might not get the detailed information or critical information from the input images. So due to this reason, we hope to extract information from not only from the final layer but also from the previous layers. In order to fuse the information extracted from the multiple layers, and here we can use not only like the IDE, average, concatenated. So these things can be used to fuse information. However, in this work, so we find after fusing this the information from the multiple layers, we find the dimension of the fused vectors or matrix is quite large, especially if we try to build the fully connected layer before the output to the target classes. So due to this reason, we use another toolkit. So we create the VRAD. The name of a VRAD is a vector of locally aggregated descriptors. The aim of VRAD is to actually to reduce the dimension of the input vector or matrix. So this can improve the performance also and the efficiency. This slide shows the principle of the VRAD. And certainly the first is the aim of VRAD. So as I mentioned just now, and it was designed to be low dimensional. So I think the original the motivation is to generate the vector descriptor, so which can be used to store the large amounts of images. So we know currently online there are the huge amount amounts of images, so which leads to the big space to store them. So equation here you can find the equation is try to compute the similarity between the two the vectors of two images. The K is the number of the coarse clusters. So in order to use VRAD, first we need, it's like the k-means things, it's like we coarsely allocate these the images vectors or images matrix into the sum the coarse vectors, and based on vision each the coarse vector coarse cluster, and so the image vectors will be used to calculate the similarity and then to optimize the cluster vector, and then finally generate the lower dimensional the image representative vector features. So here x1, xk1, and xk2 represent the site of all descriptors in image 1 and image 2. Actually, they represent the information we extract from the multiple layers of the deep neural network. The mu k represent the centroid of the cluster. C1 and C2 here are normalizing the weights to ensure the all the VRAD descriptors, I mean the image descriptor, have the unit normalization. So actually the mu k and C1 and C2, so these the parameters will actually be optimized by the neural network itself. So we just give them the initial value. So we can, for example, mu k, so they can be the the calculate after we allocated the image descriptors into each class. We can calculate the mean value. So then we can get the mu k. So we also can cite them as the the initial number, and then the deep neural network will optimize them. For the k, so we set k manually according to the actually it's the experience value according to the target number of target classes in your task. So for us, our number of the target classes is 2. So this means here the number of the course classes to be inside is the 16 or 32. So this means different performance can be obtained when selecting the different number of the course clusters. The data set we are using and actually is from the online open to public, and it's called the MIIC. So it's actually provided by the university in Singapore. So in this data set, so we can find that there are about 4,000 images covering 2 classes. So one is the normal images, and the second is actually the images with some the potential issues. This means that anomalies. So the data set actually is divided into 2 parts. One for training, there are about 1,500 images, and the rest images will be used for testing. There are also about 1,500 images. So in the data sets, there are total about 300 the images with the potential issues. So we just divided them into 2 parts. So 140 for the images for training, and 140 this means abnormal, not abnormal, and issue. The images with issues will be used for testing. Classification accuracy. So this slide shows the classification accuracy by using the Scratch built model with a shallow neural network architecture. So this architecture only contains 8 convolutional. I cannot remember how many. Could be the 6 or 8 the convolutional layers. but it's relatively simple compared to the some of the well-known deep neural network architecture like the REST VGG 19 or and the ratio the night 50 or 101. So you can find the performance the performance curves obtained on the training and the data side and the training and the test data side. For training, yeah, certainly it's quite good. For testing, the final after the 50 the epochs, the accuracy can reach about 90%. So this slide and shows the performance after using the pre-trained model. So the pre-trained model we used is the Resident Night 50. So actually the model is trained on the image night 1000. You can find the performance is the final performance looks better than the previous one, but you can find there are some the big zigzag, the big jump and big from the poor performance, accuracy performance. I think that one of the reasons is the number of the images for training is limited, because in total we only have the 1500 images for training. This could be the one reason. So this means that when we try to fine-tune the parameters of the Resident Night 50, which has about 23 million parameters, so this could cause overfitting issue, and especially at the initial stage. So this slide and shows the performance we obtained after using the VLAD. And so also there are still the issues with the big jump, big down, big jump of the performance. As I said, this could be caused by the data limitation. I mean, the data size is small, relatively small. But we can find after using the VLAD, the performance is relatively stable. And after the 15 epochs, and the performance is quite good. I think could be can reach the 98%. This slide and shows some of the examples after the anomaly detection. So actually, and this certainly you can find it is quite good to find where the anomaly issue is. For example, the first row shows the second. And this is the most left column and shows the clean, the original image, and the second column shows the images with the potential issues like this, and this. And the third column shows the heat map. Try to locate where the potential issue is. I mean the anomaly part is. So it can accurately locate where is the potential issue. So this one we don't use small patch here. So because it's for demo things, I just used compare similarity between the vectors after using the VLAD. So this means compare the vector representative vector. So of the original image and the image with the issues, and then we can find where issue is. Yeah, so this is for the demonstration thing. Last one is the slide and shows the two papers related to the VLAD. And also it's not very new. I think it's published maybe 10 years ago, but I think they are still the interesting thing, because in my memory, several years ago, and in some of the competition tasks, the guy using who used the VLAD get the first place. So I think the VLAD is still useful in some of the applications. Yeah, that's all presentation from my side. Thank you.